Okay, preparing to live stream. Setting it up. Didn't take this long yesterday. Okay.
It does not, it says to me that you're broadcasting on YouTube, but it doesn't say that you're recording. Did you want to record?
Yeah, we will record. I'll go ahead and do that right now. There we go. Okay, so we're recording. And we are streaming on YouTube. I can see that. I'm going to check the link. Go to link. And the link is working. Great. Okay. Okay. And I'll email Safan, let her know. Okay. And so add in the lover of Legos, because we got to do that. If you're going to put, if that's the picture you send, I got to mention it.
Well, yeah.
Yeah, and I'm sure you won't be alone. I quite like Legos, but I'm not one of the real aficionados, I know.
I'm not the super intense one either. I do own a lot, but my kid has more, right? And I do have the excuse of my kid.
Yeah, see, there are some good things about having kids. Okay. Safan waves hello. She said she waves hi to me, but we'll share that with everyone as we get things going. Let's see here. I've got to go to. And we have Guy Jett, who is kind of an astronomer type out in Arizona, who's hoping to join us. Oh, okay, and he got in. All right. So do we go with interesting banter until we start the talk, or?
I don't know how much interesting banter I can come up with.
Yeah, been a long day for you as well, I take it.
It's been a busy week.
Yeah. Well, yeah, you've been virtually flying all over the country to give talks.
Yes, beaming in and then beaming out again.
Exactly. Yeah, that was a really nice talk on in Alaska yesterday. And for those of you who are joining in for the cheerful banter, Dr. Rebull had a wonderful talk up at, where was that in Alaska?
University of Alaska Anchorage Planetarium. So it's the same talk that I'm giving tonight, just in a different recently added state.
Yes. So you got the 49th and 50th.
Exactly.
All right. And well, we've got a few people, not too many, but we've got so far 7 people watching on the YouTube. And for those of you who are already on the YouTube, I'll say this again, hopefully later. If not, hopefully someone will remind me. But I'm going to try to keep an eye on the YouTube so you can ask questions there. But I think you wanted to save them to the end. Is that right?
Well, if you want to filter the questions and field them to me in real time, that's fine. Or if you want to collect them all and to give them to me at the end,
okay,
that's fine too.
All right, we'll see how it goes. If something needs to be asked now, maybe I'll let you know.
Sounds good.
All right. And a couple more minutes. All right. Put this a little bit behind me so maybe we can create the illusion. Yeah, there we go. No. Oh, yes. Kurt mentions that you should meet Dr. Roy Gal over at UH Manoa. He is a huge Lego enthusiast. And yes, I know that he has sponsored a Lego fire walk at the Manoa Open House for several
Oh my
years.
goodness.
Yeah. Okay, good. Oh, yes. And Safan Kahali has also mentioned that you can, if you're watching on like the virtual worlds, on chat as well. So that is, I'm sure she means asking questions. Those who have access to the chat, she can help get that to us. All right. And well, it is 6:30. Shall we go ahead and begin?
Sure.
Kind of unusual for something to start on time in Hawaii, but I think we should. So welcome all. It's not quite the same, not having you all in the conference room here, but welcome. And we're going to give a shout out to all of our friends out in Oregon who are kind of being virtually hosted by Safan. And I'm Dr. J.D. Armstrong. I'm the Maui Technology, Education, and Outreach at the University of Hawaii Institute for Astronomy. And so one of the things I sometimes do is put these talks together. And I hope Luisa does not hear this, but I somehow conned her into volunteering to do this, and she came away with the idea that she had asked me to do this. So really great job on my part.
Well, this
Really
is
quite proud
Zoom
of
is
that.
so much cheaper than flying, you know.
Yes. Yes, so much cheaper than flying, but we're really glad to have you here. I've been working with Luisa for a few years, for I don't know how many years, several years, just a little bit pieces here on and off. And one of the programs that she runs that is how I got in touch with her is the NITAR program. Hopefully you'll give a shout out to that program.
Yeah, I have a bullet near the end.
You could have gone full splash page. We'd have loved that. All right. But any school teachers high school teachers on Maui that are interested in that, please let me know and I'll make sure that you can get in touch with Dr. Rebull. And another thing that I'll mention is that she is a huge Lego fan, not quite as big as Dr. Gell over in Manoa, but a big fan, as you might have seen in her in the picture that we used for the flyer. So Dr. Rebull is a research astronomer at NASA IPAC, the Infrared Science Archive at Caltech. She's always wanted to be an astronomer, even since she was quite little. And she received her undergraduate degree in physics from the College of William and Mary in Virginia. And her graduate degree is in astronomy and astrophysics from the University of Chicago. She has been on the science staff at IPAC since 2002. Her research focuses on the formation of young low-mass stars all over the galaxy. And by young, she means only 1 to 50 million years old. And she's also interested in understanding how stellar rotation changes over the first billion years of a star's life. So we'll all virtually clap for Dr. Rebull, and I will turn the time over to you.
Sounds great. Thanks for the introduction. So today I'm going to be talking about the universe in the infrared, and specifically Spitzer's final voyage. So I'll start at the beginning with what is infrared, and then I'll talk a little bit about Spitzer, the spacecraft itself, how it works, and a lot of the engineering behind it. And then I will give a very highly biased and incomplete list of some of the discoveries Spitzer has made. Like JD said, I study things in our galaxy, so I tend to be more interested in the closer things than the further away things. So the things that I'm going to highlight are all things that are relatively close to us. And then I'll wrap up at the end with a couple of slides on how you too can play with Spitzer data. So NASA has lots of space-based telescopes, but only 4 of them are special enough to be called great observatories. There's the Compton Gamma Ray Observatory, which is no longer with us. It's re-entered the atmosphere. There's the Chandra X-ray Observatory, which is still observing in X-rays. There's Hubble, of course, which is still observing in the optical. And then there's Spitzer, which is no longer observing, but when it was observing in the infrared. So you see these great observatories by design cover a wide range of types of light. Because astronomers, for the most part, are studying things we can never go visit or even turn around and see from a different angle, we have to take advantage of all of the light that we get from these objects, not just visible light. So here I have the same little galaxy in many different wavelengths. And you can see right away that there are things that are bright in some wavelengths that are dark in others. And you can see there are some similar patterns, but then there are some things that are very different. So here, the one on the left here is an X-ray image from the Chandra X-ray Observatory. This is a UV image from a spacecraft called Galax. This is an HST image in the optical. This is an image in the near infrared, which you could construct something like this from an all-sky ground-based survey called TMAS, but this particular image is actually involving Spitzer data. And then the far infrared, you could use Spitzer, or you could use data from a European mission called Herschel. So the light is very different across all of these bands. So in X-rays, the photon wavelength is only about 2 nanometers. A nanometer is a billionth of a meter. So itty bitty photons. And for things that are thermally emitting, things that are emitting this kind of light are like 1,000,000 Kelvin. So we're talking like black hole accretion disk kind of hot, okay? In the ultraviolet wavelengths are maybe 200 nanometers. So temperatures are like 15,000 Kelvin, which are the hot stars, which are also the young stars. In the optical, you've got wavelengths of light that are maybe 500 nanometers or half a micron. A micron is a millionth of a meter. And the temperatures are maybe 6,000 Kelvin. And this is sort of run-of-the-mill stars like our sun. In the near infrared, the wavelengths are like 1,600 nanometers or 1.6 microns. You're looking at things that are like 2,000 Kelvin. These are the very cool stars, which are also usually the old stars. In the far infrared, the wavelengths are like 100,000 nanometers or 100 microns. We're looking at things that are maybe 30 Kelvin, and that is the cool dust that's heated by the hot stars. So lots of different astrophysics across the electromagnetic spectrum. We at IPAC have a very biased view of the electromagnetic spectrum because we are very focused on infrared light, and that's where the cool stuff is. So here I have, this is the beginning of a series of pictures that are going to compare visible light and infrared light. So I've got a little dog on the left in the visible, and then on the right in the infrared. Now there's two really important things to know about this infrared image. The first is that I think it's appropriate to call it a remapped color image. Sometimes you hear people referring to this as false color, but let's be honest, language matters, and false color makes it sound like I'm hiding something, but I'm not, because a true color infrared image is super boring because we don't see infrared. So I absolutely have to take those infrared photons and translate them into color that I can see, in other words, optical. So remapped color is a better term than false color. The other important thing is that the way I'm going to translate those infrared photons corresponds to a temperature scale. So in this infrared image, things that are black or blue are cooler, and things that are white or yellow are warmer. So you can see that his water dish here is cool. He's a fluffy little dog, so there's a halo of cooler fur around his face. His ears are warm. His face is very warm. His eyes are very warm. But he's a healthy little dog, so his nose is cold. So now you know that hot things glow in the infrared. Which one is the hot water? It's the one on the bottom. You can see the base of the faucet heating up. You can see the basin heating up. And even though the hot water is on, the base of the cold water faucet is still cold. Now you know that infrared can reveal things that are hidden in visible light. What do you think this is going to look like? I can tell you the hairdryer is on. I love this picture. You can see the heating elements in the hairdryer and even the turbulence in the hot air that it's blowing out. Turns out infrared can see through some things that are totally opaque to visible light. This is just one of those like green yard waste garbage bags, and you can see straight through it in the infrared. And it turns out that you personally are actually really grateful for this particular property of infrared light, because if you are unconscious in a burning building, one way the firefighters might find you is using infrared cameras. Even small fire departments often have infrared cameras for specifically this reason. Once you know the firefighter is there, you can kind of see him in the smoke. But if you didn't know that the firefighter was there, he would be hard to find. Right? But in the infrared, he's really obvious. And you can tell that he's got an apparatus that's helping him stay cool. And given where that hose is going, probably it's carrying oxygen as well. So I live in the foothill communities around LA, and all what that means is we're up against the hills, and it's very dry here. And so all of these little foothill community fire departments, almost all of them have infrared cameras on helicopters because they're looking for fire in the hills. So it's a big deal here in LA. Some things are transparent in visible light, but are totally opaque in the infrared. Here's a set of French doors in my living room. That door is open, this door is closed, and you cannot see through the glass in the infrared. And this, incidentally, is why when you park your car in the sun, you have to drive like this, because the sunlight comes into your car through the windows, heats up the inside of the car, which then re-radiates in the infrared, but the infrared can't get out because it can't get through the glass. So that's why your car gets so hot. So the next time you can't touch your steering wheel, think of all of the infrared light that's trapped in your car. So all the things I've shown you so far have sort of been everyday objects. Now we're going to sort of leave the everyday regime. I have something here called a dewar. It's just a fancy word for a thermos bottle, and it's got liquid nitrogen in it. Liquid nitrogen is clear. So in the optical, it doesn't look terribly remarkable. In the infrared, I mean, liquid nitrogen is 77 Kelvin. So in the infrared, it's actually colder than the camera can see. So it just gives up and colors it black. But now I'm going to add frozen peas to the liquid nitrogen. So even though the frozen peas are very cold, they're warm compared to the background. So you can see them in the infrared, and that's what's going on in space. Even though some of the things that we study are very cold, they're warm compared to the background. So they glow in the infrared. Here's the familiar constellation Orion. And here's what it looks like in the infrared. How much you miss if you limit yourself to just the optical. You might know that the Sword of Orion is a cauldron of star formation, but I bet you didn't know it's part of the same star formation epoch that there's stars forming little older stars now around Orion's belt. And you can probably see this circle that's here. Whenever you find bubbles like this in the interstellar medium, the fluffy gas and dust stuff here, whenever you find bubbles like that, it means something exploded. So almost certainly there used to be a star near Orion's head, which blew up. It went supernova. And the leftover shock wave is still pushing around the gas and dust, creating that bubble. So why do we need to go to space to do infrared astronomy? Well, the number one reason is that space is cold. If you're studying infrared astronomy, you're looking for tiny little bits of heat. And so your telescope needs to be cold. You can, if you pick your telescope and your mountaintop very carefully and put it in a very high dry place like Mauna Kea, you can observe from some infrared wavelengths, but observing in the infrared from the ground is like observing in the optical with a telescope made out of those fluorescent cylinders, those fluorescent light tubes, because your telescope is glowing. And so it's very hard to observe in the infrared from the ground because your telescope is glowing. If you're a gamma ray astronomer, an X-ray astronomer, or a UV astronomer, you have to go to space. You don't have a choice because that light doesn't make it down to the ground. But if you have the visible light, does make it down to the ground. And again, if you pick your wavelength very carefully, you can observe in some bands of the infrared from the ground. All those absorption bands are coming from things we really like water and oxygen and carbon dioxide. All of those things are important for life as we know it. So I'm glad we have those things, but it makes it hard to do infrared astronomy from the ground. In the mid and far infrared, you have to go to space. And then just to finish the thought, the radio makes it down to the ground. So this is Spitzer's launch in August 2003. This is really what it looked like. If you've never been to a launch, the Cape Canaveral is actually a big complex. And when you see pictures of people watching launches, they tend to be seated in like stadium kind of seating. And all those stands are near the manned mission launch pads. There turns out to be many more unmanned mission launch pads, and there's no convenient stands near those. And moreover, the particular launch pad that Spitzer launched from is about as far south as you can go in Cape Canaveral. And so the best place to watch is actually not from the Cape itself, but from a fishing pier in a park just south of the Cape. So this is really what it looked like in the middle of the night in August 2003. There's a fishing pier with like 200 screaming crazy astronomers and half a dozen really annoyed fishermen. So this is really what it looked like, fishing poles and all. But this launch was more than 16 years ago now. It's hard to believe. The spacecraft was named after Lyman Spitzer. So this name was chosen from more than 7,000 entries submitted to NASA. NASA has done this a lot, even more so recently. Every time they have a mission or a robot they need to name, you can submit your suggestions in a contest, and they'll pick a name out of the contributed suggestions. And so this name was chosen from more than 7,000 entries submitted for this spacecraft. Professor Spitzer is no longer with us, but he was a very smart guy in a lot of different ways. But the thing that I always remember about him is that in 1946, he was the first to propose putting a telescope in space. Let's think about that. In 1946, the only things that we as humans had that could really be called rockets were German V2s. And yet he had the vision to say, let's get the warhead off of there. Let's put a telescope on top and see what we can see if we get up above the atmosphere. He was a primary force behind getting Hubble funded and launched. And it turns out that he studied the interstellar medium, the gas and the dust between the stars, which is something that Spitzer, the spacecraft, sees a lot of. So Spitzer, the spacecraft, the original design for Spitzer looked something like this. It was relatively big, and the design was based on a mission called IRAS, the very first all-sky survey in the infrared, had flown in the 80s, and that design seemed to work. So the first Spitzer design looked just like that original IRAS satellite. So you can see here, it's got the telescope completely inside a bath of cryogen. So the cryogen is going to keep the telescope cool. But it's hard to build and test a telescope that has to be so cold, so entirely cold. And you see, it's a relatively big spacecraft, and the bigger the spacecraft is, the more expensive it is to launch. So there was a bunch of budgetary issues, and Spitzer was seriously at risk of being canceled. But some really clever engineers figured out how to redesign the spacecraft. So here we have the telescope exactly the same size as the original design, but the spacecraft itself is much smaller, and the cryogen is now not encompassing the telescope. So the cryogen in here cools off the telescope by exhausting the cryogen past the telescope, cooling it off as it goes. So this made it much cheaper to build and to test, and much cheaper to launch. And so that meant that Spitzer didn't get canceled and could move forward. It also turns out Spitzer has no moving parts, essentially. So that also makes it easier to build and test. Here we have a picture of Spitzer, the spacecraft. So it's not a very big thing. Here's the solar panels. The light comes in the top. This is the telescope itself. This side is painted silver so that any little bits of energy, light, heat that get past the solar panels get reflected back. And then here on the right hand, or on the right hand side of this picture, but on the far side of the telescope, that's painted black so that it can passively radiate any heat away into space. Down here is what the engineers call the spacecraft itself. That's all the electronics, all the engineering, all of the communication, all of the, the ways that the telescope actually stores the data and transmits the data. So the light comes in the top, the telescope is in here. This is where the instruments live, and the cryogen is down here. And then the antenna that's used to communicate with Earth is down on the back of the satellite there. So now I have a series of screen snapshots from something, a web application called Eyes on the Solar System. If you haven't found this yet, you should go looking for it. It's pretty cool. You can zoom around the solar system and see where all of the satellites and all the robots are, where all the rocks are. You can, speed up time, slow down time, scroll it back to the day you were born, anything you want, right? Lots of cool things that you can do within this, but I'm going to use it to show you some of these different orbits. So this is the Hubble Space Telescope. Earth is looming quite large there, and the orbit that it has is actually called low Earth orbit. The reason it has this orbit is because the whole point of Hubble was to have it be serviced by the space shuttle, and the space shuttle was only able to reach low Earth orbit. So that's why Hubble is in that orbit. The disadvantage, though, is that, oh my gosh, Earth is big. And so Hubble spends a significant fraction of each orbit simply trying not to look at the Earth, because the Earth is so big from its perspective. There are a lot of satellites in low Earth orbit. You can see I've added some satellite tracks here. There are just a few of them that I'm showing here. Now we're going to zoom out. We're starting to see more of these satellites. There's the Hubble orbit there, but where do the other telescopes live? This is the Chandra X-ray Observatory, and it actually has a very long elliptical orbit. It goes a third of the way to the moon, actually. So it's got a very long elliptical orbit, but it's still orbiting the Earth. We're going to zoom out even further. If you have really sharp eyes, you might see that there's two satellites there called Van Allen Probe A and Van Allen Probe B. Those two spacecraft are studying something called the Van Allen belts, which are belts of charged particles stuck in Earth's magnetic field. And most spacecraft try really hard to avoid those radiation belts, especially for telescopes like Chandra, because Chandra's optics are designed to focus high energy photons, X-rays. And in terms of physics, high energy photons might as well be high energy particles. So when the Chandra X-ray Observatory goes through something called the South Atlantic anomaly, which is a bubble of charged particles over the South Atlantic, when it goes through that, it's focusing all those charged particles on the detector, just like it focuses X-rays. And that is no good for the electronics. So those radiation belts can be very harmful to spacecraft. And you have to worry about that when you're planning the engineering. We still haven't found Spitzer, though. We're going to zoom out even further. So this is kind of sort of roughly now. There's the sun in the center. There's the Earth up there. There's Mercury and Venus. Here's Kepler trailing away from Earth. And then here is Spitzer, even further away from Earth. So you see, it's actually quite a long way away from Earth now. So this was right after launch. So basically we kicked Spitzer out from the Earth with just enough energy to leave the Earth-Moon system. And so it just continuously trails away from Earth with time. So it's orbiting the sun, just like Earth is. It's not orbiting Earth, it's orbiting the sun. So this is 5 years after launch, which was how long it was supposed to last. And you see it's much further from Earth than it was before, but it's still relatively close. But we were able to keep running Spitzer even, many years past its nominal life, more than twice as long as its nominal life. So here are the main takeaway points from all of those slides. Hubble orbits Earth, very close to Earth, in fact. Chandra orbits Earth, but in a long elliptical orbit. Spitzer, however, orbits the sun, not the Earth. And Spitzer is trailing slowly away from us. This orbit is a really good thing because we're not so close to the Earth and the Moon, which means we don't have to spend a significant amount of time trying not to look at the Earth or the Moon. We can spend most of our time doing science. Out where Spitzer is, there's no Earth radiation belts, so we don't have to worry about damage to detectors or electronics that come from those radiation belts. It also turns out to be a really good thermal environment. It allows Spitzer to cool off just passively without even trying too hard. It can cool off very efficiently, being away from the Earth and the Moon. So cool really is critical when you're doing infrared astronomy. The Spitzer was launched in August 2003, and it was supposed to last 5 years. It actually lasted 5.5 years with the cryogen on board, and it was operating at below 12 Kelvin between 2003 and 2009. And so that was awesome, and that fulfilled its nominal mission. But the engineering on the spacecraft is so good that even though the spacecraft, once it ran out of cryogen, pretty quickly warmed up till about 28 Kelvin, that was still cool enough that we could still observe in the shortest 2 channels that we have on Spitzer. So there were 3 instruments on Spitzer. When it warmed up, the telescope starts glowing. And so 2 of the 3 instruments could no longer see. They could just see the warmth of the telescope. They couldn't see anything else. But of that 3rd instrument, they had 4 cameras inside, and 2 of them still worked great, just like they did before. So we were able to continue to do all sorts of fabulous science through January of this year. So there's more than 16 years of data to mine from Spitzer. So connecting the dots from the last several slides, we've got an Earth trailing orbit, and it needs to be cool, and it has no moving parts. What that means is that it has to turn, the whole spacecraft has to turn to point its antenna to Earth in order to talk to us. But the antenna was only designed to last for about 5 years because that was how long the mission was supposed to last. So it wasn't designed to scream into the darkness. It was designed to just sort of yell. And now that the spacecraft is further and further and further and further and further away, it's harder and harder and harder to hear it in the radio. So it creates a natural end to the mission. So this cartoon has Earth and the sun stationary. And so we're just going to look at how Spitzer moves with respect to the Earth and the sun. So when Spitzer was launched, it was right close to the Earth, and it was continuing to trail away. And when it ran out of cryogen, it was about here. 10th anniversary is here. We had the official beyond Spitzer Beyond phase started here. And the reason we had to change the name is look at how different the geometry is. Here, the antenna is pointed at Earth, and the solar panels are still pointed at the sun. So it can still charge its battery while it's talking to Earth, and everything's great. But by here, look how far over it has to tilt in order to talk to Earth. Now the sun is shining on the spacecraft, which is no good. And the solar panels are now tilted somewhat away from the sun. So the analogy would kind of be when you're trying to use your phone to navigate someplace you haven't been and you're running out of battery. You're like, oh, please just hang on till I get there. And you get where you're going and you find a plug and you plug it in. You might notice that your phone warms up when it's charging, especially when it's almost drained. So near the end of the mission, that's what we were kind of dealing with, because not only were we returning to talk to Earth, warming up the spacecraft and making it hard to charge the batteries, basically we used the entire battery charge to talk to Earth for as long as it could. And then, hang on, I got to recharge. And so it would have to slew back and then charge the battery. And we would have to wait for the spacecraft to cool off, not just from having the sunlight directly on it, but because the batteries were now charging, you got heat from the batteries charging. So we became a little bit less efficient just because we had to manage all of these resources. So here's a movie, again, kind of trying to show you that process. Here's the sun, here's the Earth. This is Spitzer turning to talk to Earth. And this was not long after launch. So it's able to talk to Earth, no problem. A year later, we're going to keep going and keep going and keep going and keep going. And you see just how far over it has to tilt to talk to Earth. Yikes. So there is a natural end to the Spitzer mission, sadly. So what do we study with Spitzer? The somewhat snarky answer is the old, the cold, and the dirty. So some of the very oldest galaxies at the very edge of the universe glow in the infrared. Lots of things that are very cold glow in the infrared. And there's lots of dust. And so that's the dirty stuff that we're looking at. So some highlights of some results. We're going to start with the solar system. You probably know that Saturn has this gorgeous ring system, but you might not know that it has a gigantic, fluffy ring, much larger than the rings you think of when you think of Saturn. That little pixel in there is all of Saturn and its glorious rings. But Spitzer discovered that there's this giant, fluffy ring around it. This ring is so tenuous, so diaphanous, that if you were standing in it, you might not notice. But because it's dusty, it's warm, and so it glows in the infrared. So Spitzer could see it. Spitzer didn't look at the whole thing because it covers a huge amount of sky. It covers 2 full moons across on our sky, but it could observe parts of it. And so we could deduce that it's there. This ring is tilted 27 degrees from the rest of Saturn's rings. And it's one of its moons called Phoebe orbits within this dust ring and probably is producing the dust that's creating the ring. This ring was thought to be there, but no one had discovered it before Spitzer, because another moon of Saturn called Iapetus is dark on one side. So sort of like when you go on a road trip, your windshield gets covered in dead bugs, but not your rear window. That's because you're going face first through the bugs. Well, Iapetus is going face first through the ring. And so one side of it is dark and one side of it is not. And so for years, it was proposed that there must be something there that Iapetus is moving through, but we didn't know what until Spitzer found it. So this is another view of it. So there's Saturn in there. Titan is in there too. Iapetus is a little bit further out in the inner edge of this ring, and there's Phoebe in the middle of this big dust ring. So some cool things that Spitzer discovered in our galaxy. So in order to explain how Spitzer knows what we know, how we know what we know about the structure of our galaxy, I have to go on a little bit of a digression. I have a son, he's 12. When he was a little kid, really little kid, he was so into planes. Oh my goodness. I thought for sure he was going to end up being a pilot because he just was all about the planes. And, you know, we live in California. Both my husband's family and my family live on the East Coast. So even when he was little, he was getting to fly back to visit family. And one time when he was 3, you know, we're back in the back with the cattle, right? So we're trying to get into the airplane and what have you. We get all seated, we put him by the window, of course, and we're getting ready to push back. And my kid's sitting with his face squished up against the window. I'm like, what are you doing? I'm trying to see our pilots, he says. that's how I can explain how to observe the galaxy when you're inside it. So if you imagine living on a plane, you can only really see the people in the seats around you. And eventually you might realize, oh my gosh, there's a window there. I can see out the window. I can see other planes. Well, that's cool. You pick a different window. Whoa, we have wings. All the other planes that we see have wings. So that makes sense that we have wings. All of the other planes that I see have tails. I can't see our tail, but we must have a tail because all the planes we see have tails. Okay, now we get more advanced, more sophisticated instrumentation. You can look at the other planes and see, oh, they all have pilots. Some have one pilot, some have two pilots, some even have four pilots. How many pilots do we have? I don't know. We can't see it because not only are there a lot of seats and people between us and the pilots, there's also the stupid curtain and the cabin door and what have you. So the magic, so to speak, the advantage that infrared gives you just allows you to see through all of that, to see the pilots, right? So studying our galaxy when we're in it is really hard because there's a lot of gas and dust in the galaxy, but infrared will let us see through it. So this is an artist's conception, a view of our galaxy from above or below, depending on how you'd like to orient yourself in the universe. Because we're human, we like coordinate systems that center on us. So the coordinate system here is centered on the sun because we're human. It turns out, I mean, we knew we were in a spiral galaxy. It turns out we're in a barred spiral. And Spitzer helped contribute to understanding how that bar works, where it is, and how it's interacting with the arms. And having thanks to Spitzer, we have a much better understanding of where these arms are and a much better understanding of the whole structure of the galaxy. So the survey that did this is called GLIMPSE. And the way that it worked is it took a movie, basically took a survey of the whole galactic plane. And this movie, this cone here is the view that you're seeing in this. So we're getting closer and closer and closer to the galactic center here. And as that cone is moving towards the galactic center, you can see it. Why does it keep restarting? I don't know why exactly. So here's the galactic center, right? Moving through there. We're going to keep going. I'm going to go off the edge there. So this is that same image, but printed out in stripes, right? So here's the galactic center. It's a different combination of wavelengths, so it's a kind of slightly different color scheme. Here's the center of the galaxy, and as it runs off here, it picks up over there, and you run along. As you run off on the left, it picks up on the right, and so on. This is the final glimpse mosaic, the final mosaic of our galaxy. Is enormous. Like if you printed it out at full resolution, you could circle the Rose Bowl. I don't know if that means anything to you in Hawaii, but think big stadium, right? It can circle the Rose Bowl. So, you know, that is part of how Spitzer helped us understand the galaxy, is by being able to study the galaxy all the way around and being able to see through all the gas and dust. We have a better understanding of the structure of our galaxy. So the next thing I have to tell you, I also have to take a little bit of a digression to explain. So I mentioned earlier, the first all-sky infrared survey was a satellite called IRAS. And the people that were working on IRAS were trying to figure out how to process the data. Now, scientific discovery as portrayed in the media, like on television and in the movies, sounds like eureka, you know, I figured it out, I can go running down the street. In my experience, scientific discovery does not sound like that at all. It sounds like, that's weird. Because a lot of what scientists do is to try not to fool themselves. Their first thought is not, wow, I discovered this, but more, how did I screw that up? How did I make that signal appear? How did I mess something up so that I'm seeing this? Because this is not making any sense. So the people that were trying to understand the IRAS data, One of the main measurement systems that astronomers use for brightnesses of objects is pinned on, among other things, a star called Vega. Vega is the calibrator for a lot of this. And so the first thing you do whenever you have a new instrument, a new telescope, is you go look at Vega, because it's one of the fundamental calibrators. And IRAS was an all sky survey, so they were getting the whole sky, but the people that were trying to figure out how to process the data were starting by looking at the calibrators they knew best, including Vega. And Vega was bright. I mean, really bright. Huh, that's weird. Now, how do we screw that up? So they didn't know why it was so bright. And there were about a dozen of these calibrators that were just way brighter than they should have been. All the rest of the brightnesses kind of made sense. So they set aside those 12 or so stars, and they worked on the rest of the data, and they got it out and, got it out to the community. But they still were trying to puzzle over this dozen stars that were just way too bright. And they're thinking and thinking and thinking, what is going on? Why are these so bright? I mean, if we've screwed something up, we might expect an equal number of outliers, half bright and half too faint, but that's not what they were seeing. So it just doesn't make any sense. So they thought about it and thought about it and thought about it and decided, wait a minute, maybe there's a really good dusty reason why Vega is so bright. What I'm going to show you is an artist conception. It's not, sadly, a real image, but it's probably what Vega really looks like, because Vega is a bright blue star. And it turns out it has a gap and then a very dusty ring around it. And that dust is why it's so bright in the infrared. It's intercepting radiation light from the star and heating up, and then re-radiating in the infrared. And that's why Vega is so bright in the infrared. It has a dusty disk. And the dust in that disk likely ranges over a wide range of particle sizes, from like boulders to like little particles like you find under your bed. So wide range of particle sizes, but that's probably what Vega really looks like, because it's very bright in the infrared. So this discovery by IRAS was really the leading edge of, oh my gosh, we might not be alone. There might be lots of other planets out there, but they didn't know when they were working with IRAS. There was only about a dozen stars that were like this. But Spitzer helped us understand how ubiquitous this is. So these cartoons are how stars like our sun form. We're going to start with a big cloud here. We're going to zoom in on just one clump, and it's going to start to collapse under its own gravity. And initially, yeah, it's going to fall radially in, but just because of the way the physics works, it doesn't keep doing that. It spirals in and it falls onto a disk, and then from there spirals into the central star. And for reasons nobody understands very well, but almost certainly involve magnetic fields, you get some fraction of that matter that's accreting onto the star turns around and gets ejected above and below the star. So eventually this cocoon thins out, either because it falls onto the disk or it gets blown away by the jets. You still have a big, thick disk, and you still have lots of accretion, so you still have the jets. Eventually the disk thins out and the jets turn off, and you start to form planets in this disk, all in the same plane, all going in the same direction. And then eventually you have a genuine, hydrogen-burning adult mortgage-paying star, right, with a planetary system around it. So these are like the teenagers. These are the real babies. So I'm going to show you now some Spitzer pictures from each one of these broad stages. So the people that study the very earliest stages of star formation try to find clumps that are not yet forming stars. So this little clump had been known for years as a starless core, because no one could see anything forming inside of it. So they thought, okay, well, star formation hasn't started here yet. Spitzer looked, and sure enough, there's a star forming in it. That big red blotch is a baby star forming inside this cloud. Here on the visible on the left, it's a dark cloud, but on the infrared on the right, you can see it actually is a nearly edge-on disk with huge jets coming off from the young star. This is one of my favorite star forming regions. This is NGC 1333. And you can see there's lots and lots and lots of green stuff in here. Everything that's green is a jet. or an outflow or something like that. So you have to remember that in order to untangle this is a relatively dense cluster of stars that are all kind of sort of the same age, and they're all at just the right age to be having lots of jet activity. And so you have these stars, but on the time scales on which you see these jets, the stars themselves are moving. So you can have a situation where you've got a rotation axis and a magnetic axis that's inclined. So as the star is rotating, the jet is precessing, and so it may cough and spit out something in that direction, but then keep precessing and then cough and spit out something in that direction. And the stars themselves are moving with respect to each other. So keeping track of which of these green blobs goes with which star is not at all trivial. It's complicated. This is a Hubble image. It's the most popular image downloaded from the Hubble website. It's the Eagle Nebula, or M16. These three pillars are the talons of the eagle. And this image is frequently called the pillars of creation, because what's going on is you've got a bright star or group of stars above it in this picture, and they're putting out so much wind and radiation that they're actually pushing the gas and dust around, sort of like mud in a stream. They're, the places where the mud is less dense get washed downstream, and the chunks of mud that are more dense stick around longer and are able to resist the water flow longer. So that's what's going on. We've got these three clumps of relatively dense interstellar medium, gas and dust, and then the onslaught of radiation from the stars is pushing around the gas and dust. So these three pillars, they may be forming stars, but there's lots of really cool structures in there too. So Hubble has a relatively tiny field of view. Spitzer is really good at doing pretty large areas. And so here's that pillars of creation image, and here's that funny footprint. And here's what those pillars look like when you look at them in the infrared. So the Spitzer image here is data from between 4.5 and 70 microns. So the red there is all cool dust. And the best explanation that we have for why that 70 micron emission is where it is that there has been a supernova that's gone off here. And the supernova shockwave is part of what's crumpling those towers. This is another one of my favorite star forming regions because it's my data. So on the left, I've got visible again. On the right, I've got infrared. This is called the North American Nebula. Can you kind of see the East Coast and Florida and the Gulf of Mexico here? The Mexican Riviera here. The Pelican Nebula is harder to see. Here we've got the head of the pelican, the beak of the pelican, his belly, and this is kind of the back of his neck. I love the infrared image of this because it looks totally different. I promise you, they're aligned the same way and they're covering the same chunks of sky. The back of the pelican's neck here is this right here. The Mexican Riviera right here is that right there. And the Gulf of Mexico here, that's so dark, turns out to be another cauldron of star formation with hundreds, if not thousands, of baby stars forming within it. Here's a zoom in on part of it where the inset is a slightly different combination of data, but you can see all those little red blotches are baby stars that are forming in the Gulf of Mexico. And yep, I get to name them. They're relatively boring names though. They're just the position of them. So it's just a long, basically phone number kind of thing. You can see there's little bits of green in there. Those are outflows from some of these baby stars. So I haven't shown you any spectroscopy yet. Spectroscopy breaks up light like a prism does. And when you do that, you can see what the matter is that's emitting that light. And so here we have brightness as a function of wavelength. And the top spectrum is of a disk around a star that has the relatively boring name of HD 69830. And all of these bumps and wiggles are real. That's not noise, that's real data. And the brighter green sections here is a dead giveaway for olivine. And I know that when I say like green sand beaches where in Hawaii, that you know what I mean. That's olivine. So that green mineral is found in the outer disk of this star. The spectrum on the bottom is from comet Hale-Bopp, which was a gigantic comet in our solar system that came in to visit the inner solar system from the outer solar system several years ago now. But look at this one's spectrum. It's got all the same bumps and wiggles that this one does. So whatever comet Hale-Bopp is made out of, The disk around this star is also made out of the same stuff. So Spitzer increased the number of stars that we know of by many factors of 10. So now we have a much better understanding of the interactions between the clouds and the stars, how stars cluster, the timescales of star formation, all the different stages of star formation, much better understood now thanks to Spitzer. And importantly, there are planet-forming disks everywhere. So it's not at all a surprise that we're finding that so many of these stars have planets. So in the little bit of time I have left, I'm going to talk a little bit about exoplanets. So in general, Spitzer doesn't discover planets, but it helped characterize planets or find more planets. So there are basically 4 ways to look for planets. One is the radial velocity method. So while your mental image might be that Jupiter goes around the sun, it turns out they both go around the center of mass. So every time Jupiter orbits, it tugs on the star a little bit. And when you are observing planets in other star systems, even if you can't see the planet, you can see the star wobble. So you know that the planet must be there. That's called the radial velocity method. You might have also heard of the transit photometry method. There's where you're watching brightness as a function of time. And as the planet moves across the star, you see a tiny little dip from the fact that the planet has blocked the star's light. And so from that transit, again, you're not looking at the planet directly, but you know it has to be there because there's something that's going across the star's disk and making it slightly fainter. Microlensing is a little bit more obscure. In order to do this, you have to have a background star, and then you have a host star with planets in between us here on Earth and the background star. And because gravity is actually bending space, it distorts the light coming from behind it. And so when this planet, or this star and planet system moves in front of the background, you can watch how the star brightness from the background changes. And then again, you can guess that there's a planet there. The easiest to understand without too much work is the direct imaging way, but it's also one of the hardest things to do when you're looking for planets. It's kind of like trying to image a mosquito flying around one of those big spotlights that you see like on Hollywood. So here, in order to make this work, you have to do special things to get rid of the star, right? So that X is where the star was before they processed the data. And here we have 3 planets around that particular star. So Spitzer was really good at those 2 things, the transit photometry and the microlensing. So this video has demonstrating the transit method. So when I was just explaining it, I had the planet going in front of the star. But in the infrared, what really matters is the planet going behind the star, because the planet is often pretty bright in the infrared, at least compared to the star. So when the planet goes behind the star, you see a tiny little dip, which means that we're seeing photons from the actual planet, which is pretty cool. This is the first 2 observations with Spitzer that were like this. Spitzer was not designed to do this at all, but Spitzer was such a phenomenal machine that was able to do this. So here we've got brightness as a function of time, and these tiny, tiny, tiny little dips are the signatures of planets around these stars. And that's pretty awesome. Another big discovery in exoplanets was Trappist-1. So this picture is an artist's conception, but it's kind of foreshadowing of what I'm about to tell you. It's got a lot of planets. We've got water vapor near the star, got liquid water further out, and ice further out. So Trappist-1 is a relatively small red dwarf star, not too far away from us. It's only about 40 light years, but it is tiny. It's only about 1/10 the mass of the sun. And so it's much more like a Jupiter than our sun, right? It's pretty small. It's about the size of a Jupiter. The astronomers that discovered it are Belgian, and so they named their telescope network Trappist after some Belgian beer, and they reported finding 3 planets around this red star, but they were using telescopes from the ground. So they came to Spitzer and asked for and got about 6 hours to study this system with Spitzer, because the star is so faint in red. It's a lot easier to observe it with Spitzer than it is with the optical. So they got the time to go learn more about the planets. So initially, they were pretty sure that there were 2 planets and maybe a third, but they weren't sure. So when they got their Spitzer data back, you know, they had also marshaled huge numbers of other telescopes to help. And the transits they got were bizarre. It didn't make any sense. Huh, that's weird. How did we screw this up? What did we do wrong? Huh, well, maybe we didn't do anything wrong, and maybe that's what the transits really look like. Because it turns out there are many, many, many planets in this system. There are a lot. So they came back to Spitzer and said, please, could we stare for 20 days to try to untangle what's going on with all of these planets? Because Spitzer's orbit and its stability and its sensitivity just made it ideal for this study. So we worked really hard with the astronomers to try to minimize the interruptions and tried to make it as continuous a 20-day stream of data as we could. And they also marshaled huge numbers of other observatories to also stare at it. So in 2017, they were able to say, yeah, it's got a lot of planets. Here's this little tiny red dwarf star with 1, 2, 3, 4, 5, 6, 7 planets around it. And the naming scheme is a little bit sad. The star is A, the first planet that's found is B, the second is C, and so on. So ton of planets around this little star. But this little star and its planets are very different than the solar system we know. So here's the inner solar system where the orbits are to scale, the planets are not. But you see that the entire TRAPPIST-1 system can fit well inside Mercury's orbit. In fact, TRAPPIST-1 is much more like Jupiter and its system. The Jovian system with Jupiter and its 4 big moons is much more like the TRAPPIST system than our solar system is. But of course, the science never stops. They came back to Spitzer and said, please, the 20 days went so well. Can we get 1,000 hours? Wow, 1,000 hours of continuous Spitzer time. That's a lot, okay? But they got it, and we worked really hard with them to try to make it as continuous as possible. So they were gathering more data, and now we know more about this TRAPPIST-1 solar system than any other planetary system, except for our own solar system. So this is what they were actually observing. Here's brightness as a function of time, and all those little dips are coming from all of these planets. The different colored letters correspond to these colors and letters here. And the reason that the transits looked weird before is because these planets are so close to each other that they tug a little bit on each other. And so the planets are all in resonances. And so you end up with them lining up sometimes. And so you end up with multiple transits on top of each other like this. If you were able to actually stand on one of the planets, the other planets in that system would be really obvious. They would dominate your skies. And that might be what you would really see if you were able to stand on TRAPPIST-1e. This is an artist's conception from a series of planets called the Exoplanet Travel Bureau. Those are really cool. If you haven't found those, I suggest you find those too. So in the few seconds I have left, gravitational microlensing is a little bit more obscure. Here we've got a background star, a star with a planet, and the brightness that we're measuring as it moves in front of that background star, you get a tiny little bump on the shoulder here. Let's get it here. You get a tiny little bump on the shoulder that's betraying the presence of the planet. So when you try to do this from the Earth and you do all the hairy math that lets you figure this out, you find 2 solutions that are just as compatible with the data. And you get different mass and distance combinations will both fit the data. But when you observe from Spitzer, because it was such a long way away from Earth, it breaks that degeneracy. It allows us to tell exactly what the mass and distance is. So here's the brightness as a function of time. The white is the ground-based optical data, and the red is the Spitzer data. And you see you've got that peak and that shoulder. And that shoulder is the planet. So the star is about 7/10 of a solar mass. The planet is about half a Jupiter. So yeah, planets everywhere. So in the last few slides I have, we're going to go a little bit down the digital rabbit hole. All of Spitzer's data are, of course, your data too. So I encourage you to go exploring. There's a website called Cool Cosmos, which has lots of pictures of the infrared world around us. It's got pictures of celestial objects in the infrared, and it's got a timeline of infrared missions. The infrared world site, I mean, I mentioned how infrared is used in firefighting and search and rescue, but it's also used like in art restoration and in archaeology. So this is my last slide. I'm going to leave it up for a while because it's got references to all the things that I was talking about. So the first website there is the main Spitzer website. And I encourage you in particular to check out the IR relevant or irrelevant astronomy videos. And another series of videos that we have is the Universe Unplugged. And so both of these video series often involve stars from Hollywood in helping us explain these astronomy concepts. The third bullet there is the website that goes with the end of the Spitzer mission. I mentioned the Cool Cosmos website, that's there. If you have a VR headset like an Oculus, you can search for exoplanet excursions and then wander around the TRAPPIST-1 system. Even if you don't have a headset, you can still go to YouTube and you can use their interface to wander around the TRAPPIST-1 system. I mentioned the Exoplanet Travel Bureau. They have lots of really cool posters that you can download and print, but it also has an interactive website, which is pretty fun. I mentioned the Eyes on the Solar System. That's the one where you can fly around the solar system, speed up time, slow down time. There's also an app called NASA Selfies where you can take a selfie and it will put you in a spacesuit in front of some Spitzer images. For those of you who like dead tree archives, there's a book that's recently been published by Werner and Eisenhart that's called More Things in the Heavens. And that is a summary of Spitzer, the mission, and a lot of its discoveries. And then finally, if like JD mentioned at the beginning, if you are a high school teacher and you would like to work on actual astronomy research with me and Spitzer data, please Google NITARP and definitely apply. So I think I'll stop there and I'll take any questions you have. You're still, there we go.
There we go. Yes, I'm not muted anymore. And all right. There is a little bit of a delay between our Zoom here and the YouTube.
Not at all surprising.
Yeah, no surprise. The surprise factor 0, Captain. So we'll give people a few minutes and to see if they have any questions, and if not, we'll just say thank you. And actually, we'll give you a round of applause now. I'm sure that the others will participate in that. While we're waiting for that, I might have missed this, but how far has Spitzer gone past its original expiration date, shall we say?
So it was supposed to go for 5.5 years and it lasted 16. So 3 times the original nominal length of the mission. Wow. And by the end of its life, it was so far away. So it takes light, a considerable amount of time to get from Earth to Sun, right? Rather from Sun to Earth. And of course, the way that we can communicate with Spitzer is with light, with radio light. And it would take like 15 minutes to go talk to Spitzer and then wait for the response back. So it's a long way away.
Oh, yeah. Okay. We do have just a comment, aloha and fascinating. So I think that people have enjoyed the talk. And we'll just say thank you one more time. It's been wonderful to see you, and I think that everyone enjoyed the talk.
Thank you so much, JD. Have a good evening, everybody.
All right. Okay.